Hello community, so great that you are back. Today, one simple question. Do I learn fast enough? Let me explain. In this video, we found out that shuffling here the order of independent premises here should have only a minimal impact because in logic we have the commutativity law. However, we found out that it does have a significant effect, and we deducted that LLMs are learning order-dependent patterns in their multi-step reasoning path. So there's nothing like an emergence of intelligence in our LLMs, especially if we look at multi-step reasoning of those systems. And you remember in this video here at minute 29, we had here together this beautiful idea how to overcome this with a chain of thought now, with a structured reasoning process, with a direct acyclic graph. And we said, you know what? What about a chain of thought is not just a linear sequence of steps, but what about a structured process with dependencies? This would solve this particular problem. Now, you know what? Let's do this. Let's be brave. Let's discover new worlds. So instead here of our classical training of optimizing long, unstructured chain of thoughts and the training of those models with this unstructured chain of thoughts, let's think about what we just found out yesterday when we looked here at a precise mathematical formulation of chain of thought, and we discovered it's kind of a black box. We have no valid mathematical symbol. But again, what about we experiment with structured chain of thoughts? So let's open up here our idea shop and let's build structured chain of thoughts. Now, of course, you know that we are not just here some simple plain. No, we want to have here some good ones. So we integrate here a gradient of complexity in our structured CoTs. We will make the whole dataset modular because, yes, of course, we want to have a self-reflective and self-learning system in the end. And we will do here a reinforcement learning. You say, of course, everything is a reinforcement learning today, no? Yeah, but we will go, since we have a modularity with a gradient and complexity, we will now go with a hierarchical reinforcement learning. So, and you know, we have videos here about reward systems and reward models, and I showed it on LLMs and vision language model for robotics and everything. We know this, no? And you remember that when we went here from A star to Q and Q star here for the multi-step AI reasoning, we developed already a lot of these reinforcement learning methodologies. So let's take this. And then, then we have something special. Because if I go now with structured chain of thought, and we will build an adaptive one. Now, this is now something that I can define. I don't rely that the LLM was a syntactic data define here structured reasoning path for physics or for chemistry or for mathematics. Now, if I only have a limited number, I can control the presentation here of the reasoning path, the complexity. And this makes it now interesting because in physics, I need about 100 laws in physics here for the mathematical physics implementation. No? So I don't need to trust an LLM. I can define here, I can imprint here the logic structure on the multi-step reasoning. So, of course, hey, but not make it here a linear chain. No, hey, come on, we're here in graph theory, so let's make it self-learning. And if you're a green grasshopper, say, how can we make a system self-learning? I have a video on this, about Gödel's theorem and Gödel's EIH and the blueprint for self-learning system. So everything is available for us. We just have to have the idea and then we can code it. So let's look here for the spark of genius that we need in this video. So let's think about it. So first we build or we define here a structured chain of thought library. And we have here, hopefully human evaluated, for sure I will do it here, 50 to 500 domain knowledge specific, theoretical physics, mathematics, chemistry, biology, financial, medical, whatever you like, chain of non-linear sorts. We build templates that have structure with a strong complexity gradient. We do this in a modular form, and we call this simply chain of non-linear sorts. Beautiful. So since now I can define it and I can now control the reasoning structure of our LLM and the reasoning coherence being here with a gradient of complexity, this is now a challenging topic. But this is now exactly what we want to be implemented by the AI in the AI thinking process on our domain-specific knowledge. So we are here deep into reasoning specialization for financial jobs, for theoretical physics, for mathematical jobs. We don't just go with one model, let's say Claude Sonnet 3.7 deep thinking for 8 billion people. We go here for really specialized expert systems. And then, we have now reinforcement learning and we have hierarchical reinforcement learning. This is now a sequence of high level, we remember, chain of non-linear sort templates. And we go here the classical way. We have a base LLM to learn the optimal sort template trajectory for multiple ones. And this base LLM is guided here by a secondary intelligence and inference LLM to solve a series of simpler subproblems. We have here decomposition of a higher complexity into an n-step lower complexity problems. So we have our classical reinforcement learning policy and our reward model architecture that we know from PPO, I don't know, now more than 4 years. And you know this, no? Because I had a video where I showed you here the jump from reinforcement learning to DPO, from PPO to DPO. Now we jump back for some particular reason I'm going to explain. And you remember that for inference reasoning, the QNAT that we developed here, was this in the inference acceleration. So you say, hey, you know what? We could do this here in the TTS. We can use a novel policy reward structure that we developed in this video for a Monte Carlo tree search structure. Yes, we can implement all of this, but let's not forget, just 5 hours ago, I posted here on this YouTube channel that there is now, they developed here the inside of the reinforcement learning, the PPO methodology. There's a collapse here, especially if you go for long chain of sort structures. If you have read this paper, and I think it's really beautiful, March 4th, 2024, you know our classical learning objective and our classical PPO from OpenAI developed. And then they come up with 2 solutions. So at first they identify there's a problem and there are 2 factors that contribute to the problem. And then the first solution here is a generalized advantage estimation. And you see it's such an easy correction, but it optimizes here the PPO performance here, especially for long chain of sort. And yeah, you have a look at this paper. It is really nice. So we take care about this new insight for March 4th. So thank you to ByteDance. And as we said, TTS, no? Test time compute scaling. Like Sonnet's thinking model, or 01 or 03, who all know these reasoning models. Yes, let's do this. We have the time to wait 2, 3, 4, 10 minutes for an answer, if it's the correct answer. So we have just to develop a new inference scaling system at TTS through the possibility to have an adaptive scaling in runtime. So our chain of nonlinear sort templates are here now aggregated here in real time if we have a specific query coming in and we have TTS system. Since we have a hierarchical reasoning paradigm, this simplifies now the search for the reasoning path and enhances here the reasoning ability for the complex problems by selecting the right templates. And in those templates, we have then the child templates with lower complexity. And everything, if you want, is kind of predefined on a logical level, because I know exactly how in theoretical physics I want my AI system to argue, to apply a certain kind of logic and apply a certain kind of mathematical formulas for my theoretical physics. So I'm now in control of this, and I kind of like this. So let's come here now to the core new idea. No. Princeton University already did it. We are 3 weeks too late. And you know what? They did exactly what we just discovered, what we just tried to come up with. They published this on February 10th, 2025. All our 3 steps. Now you know exactly the background to this study, and you know exactly what they did. You don't have to read here this study anymore by Princeton and Peking University, because this is one-to-one what they implemented. So sometimes the PhD students here looking here for a great PhD topic, sometimes they are faster than we are here on this YouTube channel. Okay, Princeton, you won this time. Let's have a look at the performance. And I think this is really interesting. And just look here at GPT, the O1 system, which is a huge system, and then open source LLM, and maybe just go with R-star mathematics or DeepSeek here, the version 3, and you see if we just take a 33 billion free parameter system, and we apply this methodology that we just described here, we call it ReasonFLUX, beautiful. This system outperforms here all the open source reasoning LLMs, and also here O1 mini is not really up to date, but you see it is also outperforming here a little bit the O1 mini, which is real huge. So with a dedicated 32 billion free trainable parameter system, we can outperform here our reasoning LLMs. That's amazing. But you know, we want more. We are here for the world dominance. So I have to ask, why not 100%? What is the mistake that we did? Because if you think about the logic, it should be the perfect system, yeah? Should have implemented all the mathematical rules, all the mathematical logic implementation. If the training would have been perfect, if the reinforcement learning would have been perfect, this should be not 91.2, but this should be 99.9. So you see, there's still a way to go. So if you are looking for your new PhD topic, I have some ideas for you. So what are the facts of today's video? what we had a look at. Let's do it in this way. So instead of having here the LLM generate in a boring classical way a long unstructured linear chain of thoughts that are so, I don't know, 2020, the model is now trained to select a series of predefined high-level Princeton did a linear sort template. Okay, now I understand why Princeton only achieved 91% performance. They went with a linear sort template. Okay, so you see, interesting. We had a better idea. So this linear template serve now as the building block for reasoning, exactly. And then also they implemented here hierarchical reinforcement learning to teach here the classical RL model here, how to plan the optimal sequence of the templates. So we have a trajectory that you know within our multiple steps of, if you want master template, normal template, child template, and you immediately remember Monte Carlo tree search. Model learns which templates to use and in what specific order. And we will have the reward model here that guides here the general system and leads you to a correct or efficient solution. So there's a training process, the complete reinforcement learning process. This can be quite complex given the complexity that you want to include all the solutions for. And then, of course, optimize the internal reasoning process, handle complex problems by template, yes. And it improves the efficiency and robustness. However, remember, are we still in linear? If you want, it's easy to find out. Let's say linear high-level strategies rather than relying here on potentially long-term token generation here by unstructured forms. So you see, Princeton was not really up to our beautiful ideas, so they did some simplification. However, beautiful, they published this, and we have an Apache 2 license, so you have here the complete code, you have the complete data. So let's have a look at this. This is our GitHub repo, great. There are your 10,000 lines here of the data, the template here. And they have really the description, application, and the reasoning flow. So for mathematics, yes, I have to tell you a little bit later. And then we have, of course, here the implementation. We have the ReasonFLUX Python, here the class definition, the controller definition, the dependencies, the structured reasoning, and everything is available for you. So open source, go have fun with it, implement it for your particular ideas. And then they give us here this beautiful chart. You know, they say, okay, we have a mathematical problem. And now I have to tell you, they only did this on mathematical topics, only for mathematical logic. And they said, look, we had a look here at the reasoning approach here by O1 mini. Step 1, step 2, step 3 is missing, 4, 7, yes. So they looked here at the reasoning process of O1 and they found it is not perfect. It fails to find here the correct approach for the correct solution. Then, of course, they went to their own ReasonFLUX system. And yes. And you can see here the different steps and they show, yeah, they found the right solution. But I think this information is interesting in its own, because if you ask yourself, hey, let's try to understand why OpenAI, the O1 model, failed. Why? Did O1 not have all the mathematical textbooks in the world? I mean, in the whole internet? Was O1 not able to copy the complete internet? I would say yes, they succeeded, so no problem. So they should have all those information, all those examples where we build here our linear and non-linear chain of thought structures. Or did O1 not have all the GPU clusters in the world? I mean, Microsoft at the time. Yes, they did have access to all the cluster they needed. And you know what? Mathematical reasoning is simple. If you compare mathematics to theoretical physics, math is simple. It's trivial in its complexity structure. Because we have really given pathways how to solve particular structures. So why did OpenAI fail? And why ReasonFLUX is better? Does it mean that all the reasoning models, also trained on all the textbook and math in the world, still fail? And why? So there's a lot of research topics to be discovered. But let's talk in general about the limitations. Especially here about the implementation here by Peking University and Princeton University. This ReasonFLUX. So the success depends on the quality of those sort templates, of the library, of the reasoning path and mathematics they deducted. And if you go here for a syntactic one, might be great, but you know what? If we have a limited amount of sort templates here, maybe even of non-linear, I think it would be good to invest in humans to bring up, and I will write my own sort templates here for theoretical physics, because I know how I want my system to think and operate. So quality is a topic. This here is really only focused, let's say, on one of the simplest cases, mathematical reasoning. Math only. Think about a normal human language. How many variation, alteration, permutations, and my goodness, I don't know what we have to take care of. Think about biology. Think about medicine. In medicine, we don't have mathematical formulas to follow for differentiation, integration, or think about theoretical physics here. So there is now to bring this over to a higher complexity. This will be a challenge, and you have your PhD waiting for you. And then think about here the methodology of the complexity of a hierarchical reinforcement learning training. There seems to be not yet there at 100% performance. Of course, it adds now an additional layer of complexity to the training. It takes longer, you have to pay more. But yeah, there seems to be also some optimization possible. So those limitations give us here the path into the future. Let's come to an end. Okay. Now, I looked here at the templates that Princeton and Peking University published. Those were their guiding lines. Those were their best perfect systems. Look at this. Template, knowledge tag, description, application scenario, and then the reasoning flow. And then the example with an explicit solution calculated given the reasoning flow. I think this is nice, but you know what? This is exactly like when I studied here, this is exactly like my old textbooks. Yes, when I studied, we had books out of paper. I know some of you might not guess this. This is what we did as humans, and now we have to formulate this in particular templates with increasing complexity for the stupid AI machines to learn it. Gee, there's something wrong. So this is something I don't really understand. This was in all the textbook, and OpenAI failed that their models are really achieve 100%. So there's something odd. Look at this here, at another topic. The reasoning flow, the example, the problem, and really the solution step by step here. Of course, in a linear sequence, but yes, it's only Princeton University, never mind. So we have all these step-by-step explanation, and O1 still failed to perform. So why? What is missing in this unstructured linear chain of thought training that O1 was trained on? Yes, the next generation of AI, they will have to be trained on different logics. And why did the LLM not understood here directly from the textbook? Look at this formula. Application scenario, the reasoning flow here, some trigonometric function, simple easy example or the solution, but this is what we have in the textbook. And still our best reasoning system do not reach 100%. Why is this happening? What are we missing? I think it's fascinating. And of course, if you are a subscriber of this channel, you might say, well, you are working here with chain of thoughts. And you have your own video, I think 8 months ago, where you showed us that the graph of thoughts is so much better in its reasoning performance than a chain of thought, no? It's so beautiful to have you as a subscriber. And yes, you're right. Graph of thought was never explored in this complexity. And I think if you just compare it with Monte Carlo tree search and some adaptive Monte Carlo tree search in a higher complexity level, I think the implementation of a graph structure might really be helpful to reach almost 100%. Or, we talked about here, the test time compute scaling, now the inference run. Maybe Princeton TTS was not the most optimal system, no? Or maybe it was just running for 7 minutes. Maybe it would have needed inference runtime of 27 minutes. I don't know this, but you see there's so much new research, so much new topics that you can explore, that you can try out, that you can publish, that you can go for this. And I think we are just living in some beautiful, exciting times. What else? This is it for today. Okay, so you see, Princeton University, yes, beautiful ReasonFLUX, great cooperation here with Picking University. This is amazing. So we are just some week behind here, the university research here at the most prestigious university in the world. So you see, yes, we have to come closer. We have to accelerate our learning. I have to speed up my learning. And if you want to join me, hey, why not subscribe? The next video will be published, hopefully, tomorrow.